Hello, good afternoon. I hope you had a great lunch. Next up, we have Shrayas and Rengaraj, who will be talking about no die packets, demystifying network fundamentals with Scapy. Over to you, folks.
Good afternoon. Welcome to our talk. Hello, everyone. Welcome to our talk. This talk was formed from many of our discussion between myself and Shreyas at Chennai Pai meetups. We thought it will be great to involve you all in this discussion. Myself, Rengaraj. I work for SES as a senior software engineer, and I have been using Python since 2011, and I use Python in embedded device interfacing and automation testing.
And my name is Shrayas. I head engineering at a small product-based company in Chennai, where we build softwares for book publishers, distributors, and retailers. I've been involved with Chennai Pai for the large part since 2014. You can find me on Twitter at Shreyasar. So let's start by sort of establishing the aim for our talk. More specifically, we have two aims. The most important aim is that we want to foster conceptual thinking. In the age of AI, where sort of getting to the answer is really simple and easy, we believe that it's important to sort of dig deeper and look at the building blocks of how those answers come about. The way to do this is to look beyond the abstractions. We're so used to calling request.get or using curl that we often overlook the amount of strong shoulders that we need to stand on to achieve that one single command. 12 years ago, when I asked a mentor of mine to teach me the basics of machine learning, he told me something that I'm just about now beginning to understand. He said, everything at the end of the day is just addition and subtraction. So our attempt here is to explore the idea of just addition and subtraction in the networking world. And what better way to start than with a story?
Consider the Earth on an everyday basis. A flight will move around the Earth from one place to another. Assume that somewhere along the path, someone inside the flight want to talk with someone at home. In reality, the message goes to the satellite and it will goes to the terminal and it will go via an ISP and then it will go to the home. Now let's say by the time the person responds, the flight has moved some distance and it is capable of receiving the reply. But when trying to send a response back, it does not get delivered and the internet goes down. In this gap, I called upon to debug the issue. Let us look at the arrangement again. This part of the network I was responsible for. I am responsible for, and I know both the flight and the ground terminal, we have firewall in place. So the first place I look are the firewall logs. For some reason, I don't see any firewall logs. So in our network, I decided to take capture at flight exit point and the terminal entry point. When I look at the packet, I could see there were retransmission packets. A client, after sending the packet after certain time, if it doesn't receive anything, it will time out. Alternatively, the capture also have reset packet. What does that mean? If the firewall doesn't know how to process a packet, it will forcefully close the connection. So the reset and retransmission, what it tells us is the firewall doesn't know how to process those packets. So what we need to do, we need to allow those IPs to pass through the firewall. So there is something called allow list, and we need to add the IPs of the users to be added in that firewall. You can ask me a question. Before that, the same flight was able to communicate to the ground. Why it is not able to communicate after some time? If you could notice, the flight has already traveled some distance. There will not be one terminal around the globe. There will be multiple terminals around the globe. We need to add the list of IPs in all the terminals around the globe. Once that is done, the next flight that goes over the same ground terminal will be able to communicate to the user. And this is the kind of thing that we solve every day as a network engineers. So with that story, let us lay out our agenda for today's talk so that we may all learn how to think as a network engineer.
So we'll start with outlining our assumptions that we'll hold for the duration of the talk. Then we'll take one single HTTP and one HTTPS request and break it down to see what happens underneath. Then we look at the protocols, other protocols, and aim to draw some conclusions from what we've learned. After this, we actually have a surprise for you that will be based on everything that we've looked at so far. And we'll end with our takeaways, and time permitting, we'll open for questions. So let's lay down our assumptions. This talk only deals with classic TCP, TLS, and DNS protocols. We know that the modern alternatives are much more sophisticated, but we believe that a classical understanding is more important for us to even appreciate the modern iterations of these classic protocols. We will take the liberty to simplify and sometimes even oversimplify some things in this talk for the purposes of conveying the overall concept. The nuances we leave as an exercise to you. With that behind us, let's look at one HTTP and one HTTPS request. The simplest way we can do that is to fire a curl request. Notice that I'm hitting the HTTP endpoint here, and my domain is ICANN_has_IP. It's a simple site that gives me back my IP address. Simple enough, I get a response. Now I have a few questions for you. Shout out the answer if you know it. How many requests was this? One. How many responses did we get? One. And how many packets do you think it involved? 10. So I made one request and got one response, but 10 packets were involved. Let's dissect. These are the 10 packets involved in making this one single request. And I understand that it probably looks overwhelming, but stick with me and we'll figure this out together. But before we do, I'm sure some of you have other questions saying packets. What are those? So let's do a quick crash course on packet capture. I'm sure everyone knows this, a simple client-server communication diagram. Now consider you want to understand everything that's happening at a client's end. You ask someone to do the spy work for you, to listen to all the communication that's going in and out. And this spy takes dedicated notes about everything that they observe. Now that would be quite convenient, right, for us to understand the happenings. This entire setup and what it yields is basically this. The important point here is that all communication goes in and out in the form of packets. And the tool that helps us to do this is a tool called Wireshark. So let's go back to our packets and understand what each column means. The first two columns represent the sequence of the conversation. Who's speaking first, who's speaking second, and the like. The third and the fourth part gives explicit addresses to those that are communicating, and these are called as IP addresses. The next is the preferred language of conversation. These are also called as protocols. Simply put, it's how we've agreed that this talk will be in English and how English has a set of semantic rules that makes it a language that's understandable to you and me. The last part is the content of the conversation, a gist more so. We can click through each one of these packets and look through more details, but we'll do that in the forthcoming slides. The idea is that what we have now at our disposal is a spy that's able to take copious notes about the happenings at the client's end. Nice. So let's come back to our 10 packets and look at them one by one. But before we proceed, I'm going to invoke our simplification assumption here and say that all packet captures from here on out will ignore the first 4 columns of name, time, source, and destination. This is only so that it's more visible to you all and we focus on the important details. So instead of looking like this, it'll look like this. And all of the packet captures will be in the repository and you'll be able to access it all after the talk. Our first focus is on this section of 3 packets. It should actually be 2, but remember what Rengaraj said. And the first packet was dropped and while I was capturing it, and it magically knew to retransmit the packet again, and that's why there are 3. These 3 packets correspond to the question, where is the server? When 2 machines are communicating with each other, they only know how to establish this communication via IP addresses. But IP addresses are hard for us as humans to memorize. So it's easier for me to remember a name than for me to remember 104.16.138.216. This IP is an unambiguous representation though of where the packets are supposed to be directed to. So as a first step in the process, the client asks an intermediate address book. Where is ICANN_has_IP, to which it receives an IP address. This is also called as the DNS, or domain name service. Basically a huge dictionary of names to IP addresses. DNS is such a painfully beautiful protocol that we can do an entire talk on it, but that's for another time. Maybe next PyCon. Then we move on to the next set of 3 packets, and this marks the start of the connection itself. The client asks the server if it can communicate. The server says yes. The client acknowledges the server's yes with its own acknowledgement. This is also called as a 3-way handshake, OR. Now after all this drama, we get to the next packet, the actual request. This is where our client is requesting for the resource at / with the method get. The server then responds back to the request and hands over the response with the ever so familiar 200 OK status code. Not so complicated now, right? Let's actually dig a little bit more and look at one single packet. More specifically, the request packet. The first thing to notice here is that there are well-defined parts to every single packet, or layers would be a better word. Think of them like a tiramisu cake that is made up of layers of mascarpone cheese with coffee-soaked ladyfingers and then a dusting of coffee powder on top. Wait, what were we talking about again? Oh, packets, sorry. Notice the correlation between the top packets and the bottom diagram. The frame is made up of different parts of the packet, and each one does its work, and they all build on top of one another additively. So looking at each part of the entire thing, while super fun, will be time consuming, so I'll just direct your attention to the fun bits in each packet. We'll start with the HTTP part of the packet. This should look pretty familiar. Most of us as programmers would have seen this or some variation of this in our DevTools. No surprises here, request method, URI, user agent, headers, etc., etc. The juicier bits, we move one layer down to TCP, the transmission control protocol. Notice the source port is something random. Did you expect this? Every single process that interacts with a server gets a randomized port. If I make this request in another terminal window, or even again, this will get a different source port too. Pretty cool, right? Also notice the amount of transmission related things that are a part of the packet here. TCP is a very reliable protocol and will retry packets if they fail somewhere, as evidenced twice. So to do all that and more, it needs to retain a lot of information, and it literally just wedges all of that as part of each packet. The last part of the HTTP packet I want to draw your attention to is the IP layer. The IP is basically the addressing layer. Now it needs basically information of where it needs to get to and where it's coming from, and that's why you see a source and destination address there. The interesting thing is that it mentions that the protocol is TCP. Does this mean that the IP addressing is so reusable that it can even support other protocols too? We'll answer this soon. To sum up things for HTTP, it is insecure. We could see the request being made and the responses will also be visible. The entire transmission, retransmission, etc. is controlled by TCP, and the IP layer controls all the addressing, while where the packets are coming from and where they should go to. With that in mind, let's look at another request to the same URL, only this time via the HTTPS variant. I get the same answer, no surprises, same questions to you all. How many requests? 1. How many responses? 1. How many packets do you think it was this time? 13. 3 more. These are our 13 packets, and let's look at them in groups. The first 2 are DNS as usual, followed by the same 3-way handshake. Rengaraj is there, so I can't shake his hand. Same as with HTTP. The next 6 packets is where we start to see the differences, and given that we switched from HTTP to HTTPS, this is bound to happen. So let's understand what these packets are trying to do and what they are responsible for. Oh, sorry, looks like I mixed up something there, but let's try again. They're responsible for guaranteeing secure communications. I forgot to decrypt the title on the previous slide, sorry. This process is also called as the TLS or SSL TLS handshake. It's a rather long dance that the client and server play with each other so that they can start communicating securely. Much like the concept of DNS, just HTTPS is so beautiful that it deserves an entire talk in itself. So the how-to of secure communication, we are not going to deal with here. And just like that, we have 2 talk proposals lined up now. Now that that's over, let me direct your attention to the small part that's piggybacked on one of the packets that was part of the TLS negotiation. This is the request. After all this dance, the request doesn't even get its own packet. It just goes as part of a last packet on a complex dance routine. I wonder if it feels like a side character in these commercial Bollywood films that has no work except just to be there. But we digress. And finally, the response. I find it fascinating that just to send a single request and response, so much of work has to be done to get there. Mind you, this happens on every single request and response from the client to the server. There might be a few optimizations, sure, but HTTPS is a stateless protocol, so everything happens again the next time another request is made. And same is true for HTTP as well. So let's look at some of the cool parts of these packets. This is the client hello packet, the first part of the TLS handshake. I want you to notice how it lies. First, it says it's TLS 1.0. Then it says it's TLS 1.2. And then later on, it clarifies it's 1.3. But why? Because when TLS 1.3 came out, the routers and the firewalls would start dropping packets that were not 1.0 or 1.2. So it lied through its nose about it just to get through the gates. And once it was through, it clarified that it was actually 1.3. Maybe the I must not tell lies only applies to Harry Potter. A little down in the client hello packet itself, there's another cool bit where the client makes an assumption that the server is going to be communicating with is a server that's modern. So it assumes this and hands over 3 keys as part of its key share extension with the hope that the server will be able to accept any of these. And sure enough, the server does accept one of these and returns it back in the server hello packet. All this is part of the one round trip time handshake, which is a very important TLS 1.3 improvement, where the attempt is to reduce the amount of time spent on the handshake. Moving on. Remember that small request piggyback? As part of the same packet, the client sends a one length change cipher spec for maintaining backward compatibility because 1.2 needed this. And then it sends a finished record containing information about the entire handshake that happened till now, but completely encrypted, thus proving to the server that they both have successfully done the key exchange. The last part of the packet is the piggyback that we spoke about. And this is the one in which the actual request resides. Notice that it's entirely encrypted and I cannot see the resource, the method, the parameters, the headers, nothing. And this is why HTTPS is such a solid protocol, right? Not only is everything encrypted at the top, it's encrypted all the way to the bottom as well. Pretty cool, right? Let's summarize. Remember this, we saw this for HTTP. Now let's modify it for HTTPS. Done. I added the S at the top and made it secure. And that's really the only difference. We went from something that was insecure to something that's secure and everything else remained the same. So what are the lessons we can take from breaking down these two requests? To me, there are two. The first one is more of a realization. As a programmer, we live on the application layer most of the days, but it's important to realize that there's so much going on under the hood. The realization humbles us to the infrastructure beneath and makes us all better programmers, I dare say, because we're truly able to see the complexity now. The second one is a lesson that everything we saw is more or less built on everything else that we saw. For example, the DNS and the TCP handshake was available whether we made a HTTP call or a HTTPS call. The point of divergence was that a few more packets in HTTPS which ensured that we got more security. The layers of abstraction are so beautifully built on top of one another, being their individual selves while learning to rely on others for their strengths.
Now we understand the building blocks of network packet. That great thing is that these are not just for web. Let us see how these same principles apply to these protocols. Let us start with the ancestors of share it, airdrop, and all these kits used these days, the file transfer protocol. The important characteristics to note in FTP is that it is insecure and it uses dual channel mode of communication. To explain, let us go and look at the packet. The destination port is 21 and we are able to see that it is in the TCP layer. Good. In the last layer, we see the protocol is as FTP in place of HTTP as we saw previously. And here I am giving a user command to get the output to get the FTP reply. So the request is user and the request arg is foo actually. So you can see clearly what is the command I have given. So that it is actually insecure. Let us dig deeper. Here I am using the request to list the content of a directory. And here is the response. You can see two things. The response is entirely plain text. Anyone sitting in the network can see what is the user is issuing the command. And the FTP server communicates entirely on a different port, 2424. That is on another channel. So the claim of it's running on port 21 and being insecure and using dual channel for communication is true. Let us move on. Telnet, the grandparent of everything that we are talking here. I'm going to go on a whim and say that Telnet is older than any of us sitting here. It was built in 1969 actually, and it was largely built to be a TCP client. A TCP client is a client which is built on top of TCP IP stack. So for example, the protocols we saw before, the HTTP, HTTPS, the HTTP, HTTPS, all those are built on top of TCP IP stack. So let's say I start a terminal and I do not use a FTP client, then how do I use? I use telnet IP port. So the port is nothing but the port 21 of FTP. It greets me with a message and then I start entering the FTP command user and pause. Then I enter into a passive mode which gives me a long tuple. This long tuple is nothing but address of the dual channel FTP server is going to communicate on. I can start another telnet client pointing to that port and start receiving those messages in another terminal. So when I issue list command here, the other terminal gets the reply. So let us look at the packet now. For the comparison, this is what we captured last time when we were using the FTP client. So now we are using a TCP client. And this is how the packet look like when we captured it with telnet. So telnet is nothing but our TCP client here. There are few differences. You can see the system commands are, but otherwise it looks exactly the same. And that is the power of having a general purpose TCP IP client. So now we are going to see SSH. So SSH was invented as a secure way of interacting with the servers, rather than to use a plain text like insecure telnet client. But it is largely, is it really secure? Here is how the packet look. When we initiate a SSH connection, on the top you have all the secure stuff where the client and server exchange keys. For all the ultra keys over here, you can see clearly the algorithm is Diffie-Hellman key exchange algorithm. And once that is done, all the communication after that is fully encrypted. We cannot see anything in the payload as the other packets because they are all encrypted. Fully secure communication. Let us now take this one step further. You remember we saw FTP, that is insecure protocol. Despite being convenient to transfer files, and along comes another protocol years later that solves the security problem. So the folks paused at that time and thought, why don't we add it together? So that's why we got SFTP. The claim is that it is the same FTP protocol, but we leverage the SSH security to send the files. So it is called FTP over SSH. Here are the SSH packets we saw on the left and the SFTP packets captured on the right. To me, this is just beauty. I will walk you through why. Everything up to this packet is almost same thing, whether it is SSH or SFTP. And only the last bits, you can see the payload bits are different. In the SSH, you can see the payload bits is smaller, whereas in the SFTP, you can see it is much larger. Because in SSH, we generally issue commands and get the output, whereas in SFTP, we may send larger files. That's why you have a payload length is different. So far we saw everything is we built on top of everything else. So the invention of SSH made FTP secure. To take that even further, we built something just for this conference. So let us look at that now. So we have a demo now. Being geeks ourselves, we thought it would be cool if we get the conference schedule on a command line. So what are the current talks and what are all the next talks and what are all the talks on a track. So we built this and we call it pi in 25. To it, we can ask three kinds of question. Now.talks, which will give us all the current talks now. And then next talks, which will give us the talks that are coming up next. And the track 1 and track 2 talks, which will give us the respective track 1 or track 2 talks. It's a pretty cool no. You can see all the outputs in this slide. So I'm sure many of you are asking an important question. So what? You are probably wondering how this relates to the talk itself, right? The devil is in the details actually. This is not just a pass some JSON file and show the command, show the output on the std out. So truthfully, the pin25 is just an alias to the dig command. Here is what it looked like. If you have used the dig command, you might have already know what is the protocol we used. So what we have built is a DNS server with Scapy to manipulate the packet. The tool passes the query and then it will reply with the answer. Let us look at the things from the packet level to prove this to you. Remember how we briefly discussed the IP addressing layer, said protocol is TCP, and we questioned it if it could be another protocol too. Turns out the answer is yes. The protocol here is UDP. UDP is not as like TCP, but it is fast, efficient, and has no overhead. No three-way handshake. Nothing, just get the work done. And here you can see the query we pass now.talks using dig command. So you can see there are three outputs here. You can next.talk, you have three answers over here. Because the current talks are three talks. That's why you have three talks over here. And in case of real DNS, what you will get? I leave it to you to go to answer. So the code to achieve this is also quite a no-brainer. Scapy uses everything in a fancy Python to make the networking stack really understandable and easy to program. Let us look at the core part of it. Remember, we are as a DNS server, so we need to construct the DNS packet. We need to set its address, source and destination IP address, as well as the UDP source and destination port. We use UDP because that is the protocol preferred by DNS server. Once the request is received, we need to flip the source and destination IP address as well as source port and destination port. Then we construct the DNS packet with the answers inside it. These answers look at the query, does some processing to find the right talks, format it, and encode it as required. Then we construct the response. In the above 3 slides, we saw IP, UDP, and DNS layers. Now, to stack it and make the response with Scapy, we can use /. It should be done in the same order as we have already seen in the packet capture. Clean and neat, right? Scapy makes it such that if you know how to dissect a packet using Wireshark, then you know how to build a packet using Scapy. And this is exactly how we build the DNS server. With that, let's conclude with some takeaways.
The first one is that now you've seen beyond the looking glass, and that there is no more magic. HTTP, HTTPS, FTP, SSH, SFTP, or DNS, you know how all of these things work underneath. Do you use GraphQL, gRPC, MQTT? You want to understand how they work? You know where to start. The second one is that now you have at your disposal a new skill. Your toolkit is bigger and you have more tools in it. So the next time you're faced with an issue that you are debugging, you have a new dimension to approach the problem from. And the third takeaway is that you have new words in your vocabulary. Someone around you mentions packets, DNS, TCP, IP, UDP, or frames, and you know exactly what they're talking about. And when you're conversing with others, you have better words now to convey your points. The last and most important, according to us, is the realization that everything is built on top of everything else. The building blocks are all in front of us, and we've only been seeing the high-level picture all this while now, and we are starting to look at the blocks that have always existed underneath. You now understand and have examples on how to build things that are strong at the base and how the real world does backward compatibility and how not to reinvent the wheel. And all that's left is to put all this together and build. Thanks for listening to us. The GitHub is where we have all of the things. So, and also, I don't know how many of you know this. Kailashnath wrote something called DNS Toys, and this is sort of where we got the inspiration to write, our the DNS server. So I'll probably leave this on. Do we have time for questions? Yeah, cool.
Thanks for such an informative talk. We have 10 minutes for Q&A. I can come around the mic.
No.
Questions?
Can we have this thing back up?
In the meantime, questions?
Yeah, cool. Yeah.
If you raise your hand, I can give the mic.
A teacher I had always said that if you don't have questions, you either understood everything or didn't understand anything. I don't know which input I want, but I'm joking.
No questions. Questions going once. Questions going twice. Great.
There's one there. Three handshake.
Hi. Like maybe a big thing. Can you brief about HTTP 3, like the different version, like what is the difference with the latest version, the HTTP 3.0 or something like that? And what about TCP and UDP involved over there?
I think it's a far longer conversation, really.
Thanks.
But it does a lot of this in a lesser amount of time, is fundamentally the ideas with newer versions of HTTPs.
What about Web3?
Web3 in which context?
The networking context itself.
I'm not too sure of what you mean. Like, in what way? Like Web3, fundamentally it's built on the same kind of protocol. So it would all adhere to the same kind of things. Are you talking about any different protocol over here?
Yeah. Are we using a different protocol or like?
I don't think Web3, I don't know. IPFS and all might be different, and that's not something that we've even looked into. But fundamentally, I think everything should still build on something that exists, that already exists.
I think the repository is private.
Sorry?
Repository is private, I think.
This one? Oh, maybe. I will make it public. My bad.
And there is another question.
Where? You can answer.
Hi, I have a small question about the FTP being insecure, or not secure basically. If, let's say somebody is doing a share it in my area, and I can see the packets definitely, right? Can we know what all files are they transferring and how many files do they have on the device also?
Yes, yes. If they have the packet capture, from the payload they can retrieve the files.
Only the files which are being transmitted,
Yeah,
or
yeah,
I can
only-
run commands also on there to list out all the files they have.
Uh, if 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 they are hacked your system and then they did the packet capture with let's say they run a command in another folder instead of your folder, whatever you are doing. If the packet capture have the payload, if they do the packet capture, definitely the files will be there.
Okay, got it.
So the idea with Scapy is also it's a really fun tool. Like you can do replays, right? So if you understand that this is the kind of packet that goes to get payload X, and you have the list commands output beforehand, then you can send effectively a Scapy packet to get you that particular thing.
Understood.
So that would still be possible theoretically.
Thank you.
Hi, I have a question. Yeah.
Yeah, yes, yes.
Oh, hi.
So there is a concept like WebSocket tunneling, right, in some HTTP website. So there, how the security works, like continuous handshakes will happen, or as you said, every request one handshake will happen, right?
Now, maybe the initial tunnel establishment, that time might be handshake will happen. Once the tunnel is established, you no need of handshake, I think.
Okay.
And not the handshake, the security part I'm talking about.
Okay,
The security part.
Okay. And I have one more question. I don't know if it's the right place to ask. Like, how about the Tor network? How the security?
Sorry, I wrongly answered your question. So after tunnel also, for each request you have to create the TCP connection, right? So once, let's say you have a VPN. VPN is the tunnel, right?
Okay.
VPN tunnel. Once the tunnel is created, your endpoint and the other endpoint will become the network, same network.
Yeah.
Everything else is same. The packet has to again go through all these requests.
Okay.
You got it?
Yeah, I got it.
So you have another question?
Yeah, I had another question. Like the Tor network, you know, right?
Yeah,
How the security, like, does the DNS apply there, or I just had a small
really I don't know about those concepts behind what Tor does. Seriously, yeah.
But we have given you the tools to find out.
No, actually, you run a Tor browser and then run packet capture and you see what is happening around.
One last question.
Hi.
Hi.
Just small question.
Yes. Big question also.
Yeah, we talked about file transfer protocol and SSH.
Yeah.
Together, I forgot what the abbreviation.
SFTP.
Yeah, SFPT.
Yeah.
So what about SCP? Is it same or?
You can go.
Okay, SCP is again a copy over SSH. It uses OpenSSH protocol. SCP also uses OpenSSH protocol.
Okay.
So you actually copy the files from one system to the another, right?
Okay,
So
okay,
it also uses OpenSSH protocol.
Okay, so both are not same.
They are the same. They are exactly the same. In fact,
I'm talking about FTP combined with SSH. Is that the same with
no.
SCP?
So when you look at SFTP, it is the FTP protocol done over SSH.
Okay.
If you look at SCP, it is literally just using the SSH protocol.
okay,
That's all.
got it.
Nothing else.
But using both you can transfer files
Got
in
it.
securely.
Thanks.
These folks would be around in the hall
Any more
if you have
questions?
more questions.
Thanks, folks. Thanks for your attention.